This is Raymond Seelove with the part 3 of the snow day makeup. This one's about pH, an introduction to pH. And to start very simply, pH, when you write it, it's important to write it with a lowercase p and a capital H. The capital H is because this refers to hydrogen, and hydrogen on the periodic table uses a capital H as its symbol. pH is really a way of measuring the concentration of hydrogen. It literally means the P here is for parts, so it's parts hydrogen. Parts hydrogen. The P is not phosphorus, and so it's important that the P not be uppercase. It has to be lowercase. This can be difficult if you're trying to write pH using a Microsoft program. It can sometimes automatically correct it, and you have to go back. Don't ever use a capital P, even if it's at the beginning of a sentence. Don't ever use a lowercase h. That's not pH. Another quick tip on not looking stupid is when you say pH, always say pH. Don't say f. I occasionally have students come to me saying, I don't understand all this f stuff. And when people call it f instead of pH, then it's a quick tip-off that you don't know what you're talking about. So let me give you a formula here. pH actually is a mathematical formula. It equals the negative log of the hydrogen ion concentration. So when I write the hydrogen ion in here, I write it as H+, and I write it inside of brackets. The brackets are a chemist's way of saying concentration of. So the formula is the negative log of the hydrogen ion concentration. I'll come back to the math in a little bit, but before I do, I want to spend a little bit of time talking about some general things related to the equilibrium constants for water. Whenever you have water present, the water doesn't necessarily just stay as water. Some of that water breaks down into ions. An H2O molecule, water, when it breaks down, produces one hydrogen ion, H+, and one hydroxide ion, which is OH-. For every hydrogen, there must be one hydroxide as long as the only thing that's there is water. So if you've got a perfect solution of just water, in terms of pH, that's going to be a neutral solution, right? If it's only water, there's no acid, there's no base, then it must be neutral. And that means that the hydrogen ion concentration will have to equal the hydroxide ion concentration. So, for a neutral solution, the hydrogen ion concentration will always equal the hydroxide ion concentration. Now, we also know something else about the hydrogen and hydroxide ion concentrations, and we know this from the equilibrium constants that chemists teach us. This equation is not really a one-way equation, it's a two-way equation. So some water will always be broken down, and you'll have some water breaking down and some hydrogen and hydroxide reforming water, and it'll go back and forth between these all the time. There will always be some certain amount that will be in this form, while most of it's in this form. Equilibrium constants are something that you probably had to calculate back in your chemistry, back in high school. and you might remember them referred to as Michaelis-Menten equations, or perhaps you remember this as calculating pKs. If you want to get more detail than what I'm going over in this, then you might want to go back into your chemistry and look up pKs and equilibrium constants. Assuming that you're willing to just take my word for it instead of going back to your chemistry and reviewing equilibrium constants, one of the things we know from equilibrium constants is that the concentration of hydrogen times the concentration of hydroxide is always equal to 10 to the minus 14 power. It just is. Now, here we've got two different equations. Hydrogen times hydroxide equals 10 to the minus 14, and hydrogen equals hydroxide, which is always true when you've got a neutral solution. So that means for a neutral solution, we know that both of these equations have to be true at the same time. If you remember from your algebra back in high school, you can solve simultaneous equations, and in this case it's easy to solve it using substitution. If hydrogen equals hydroxide, then we can just substitute this hydroxide here for hydrogen, which means we've got the hydrogen ion concentration times the hydrogen ion concentration equals 10 to the minus 14. Which is the same as saying that the hydrogen ion concentration squared is equal to 10 to the minus 14. And so we can solve for the hydrogen ion concentration by taking the square root of both sides. And if we do that, then we find out that the hydrogen ion concentration is equal to 10 to the minus 7 power. If you don't remember how to do exponents, if you've got the same base raised to a power, so in this case 10, when you're multiplying things, all you have to do is add the exponents. So 10 to the negative 7 power times 10 to the negative 7 power would equal 10 to the minus 14 power. That means the square root of 10 to the minus 14 is 10 to the minus 7. So if I take this result, hydrogen ion concentration equals 10 to the minus 7 power, and then I plug it into my original equation for pH. pH equals the negative log of the hydrogen ion concentration. Then I can actually solve for pH. So here I've just taken my 10 to the negative 7 hydrogen ion concentration, plugged it into the formula. pH equals the negative log of 10 to the minus 7. Now in order to solve this, you'll need to remember what logarithms are and how to do them. This is the common logarithm, log to the base 10. And the way logs to the base 10 work is like this. Let me give you a simpler one. Let's say you have to find the log to the base 10. I'll actually write the base here, but when the base isn't written, it's always assumed to be 10. So suppose your problem is finding the log to the base 10 of 100. What that's basically asking you is 10 raised to what power equals 100? So 10 raised to what power equals 100? The answer to that is 2. 10 raised to the second power equals 100. So the log of 100 is 2. Now, we could, instead of calling this 100, it turns out 100 is equal to 10 squared. So I could say, what is the log of 10 squared? If I gave the problem to you like this, it would be so simple it would be almost trivial. This is asking you 10 raised to what power equals 10 raised to the second power. And so the answer, even if you don't remember how to do logarithms, it's already figured out for you. The answer is 2. So going back up here, if the pH is equal to the negative log of the hydrogen ion concentration, and the hydrogen ion concentration is 10 to the minus 7, the log of 10 to the minus 7 is minus 7. But of course the pH is not the log of the hydrogen ion concentration, it's the negative log of the hydrogen ion concentration. So my pH here is not negative 7, but negative 7. In other words, it's 7. So what I've just done for you is I have proven to you that the pH of a neutral solution is 7. That may not seem impressive because every one of you came into this already knowing that neutral solutions have a pH of 7. But it's important that you know that 7 is not just a number that somebody made up. It has a real meaning to it. It's related to that equilibrium constant. And so a pH of 7 means that you've got a concentration of hydrogen ions of 10 to the minus 7. Now you might not be used to thinking of 10 to the minus 7 as looking like a concentration, so it might help to translate that. Negative exponents are really the inverse of an exponent. So this is the same as 1 over 10 to the 7, which is equal to 1 over a 1 followed by 7 zeros. 1, 2, 3, 4, 5, 6, 7. I'll add some commas in here to make it easier to read. And so what we've got is a concentration of 1 hydrogen ion per 10 million water molecules. Right? If we've got 1 hydrogen per 10 million water molecules, then we've got a 10 to the negative 7 concentration, and that gives us a pH of 7.